Okay, so good morning to everyone and welcome to this academic environment. My name is Camilo Acevedo Gerena and I will be guiding you throughout this PhD candidate. On behalf of the doctoral program in engineering at Universidad, Pedagógica y Tecnológica de Colombia, Sogamoso, we welcome you to the dissertation of the PhD proposal entitled Efficient Hardware Implementation for the Reconstructions of Contact Forces in a Smart Tactile Sensing, presented by student Maria Luisa Pinto Salamanca under the supervision of Professor Wilson Javier Perez Holguín. This dissertation has been scheduled by the academic board of the doctoral program in engineering. It is led by the Professor Germán Antonio Fernández as academic coordinator of this program, as well as Professor Jorge Espíndola Niño, who represent research groups involved in this PhD program. We also welcome Professor Mauricio Valle and Fernando Vidal Verdú as reviewers of Maria Luisa's proposal, as well as the rest of the professors and PhD students of our doctoral program that are with us via Meet. We suggest you to turn on the captions that are available on the Meet's toolbar. And of course, we invite all the people to follow us via streaming YouTube. Good afternoon, good morning, Maria and Professor Wilson. Welcome to this event. Now, we're going to introduce the rest of the academic committee. I'm sorry, I was having some issues with the presentation. I keep on. We're going to introduce the academic committee for this academic event. First, we have Maria Luisa Pinto Salamanca. Maria Luisa Pinto Salamanca holds a bachelor's degree in electronics engineering from Universidad Pedagógica y Tecnológica de Colombia in 2005. She is a Master's of Science in Industrial Automation from Universidad Nacional de Colombia in 2009. Since 2011, she has been an assistant professor with the Electromechanical Engineering School at Uptc Duitama campus. She was the head of the Centro de Gestión de Investigación y Extensión Uptc Duitama. Since 2019, she has been a student of the engineering doctoral program with emphasis in electronic engineering at Uptc. Her main research interest areas are tactile sensing, system electronics design, and testing. Wilson Javier Holguín Perez holds a bachelor's degree in electronics engineering from Universidad Pedagógica y Tecnológica de Colombia. He has an engineering master's degree in industrial automation from Universidad Nacional de Colombia. He is a doctor in engineering from Universidad del Valle in cooperation with Politécnico de Torino in 2012. Since 2005, he has been a full-time professor for the Electronic Engineering School, the Master's in Engineering and the Doctoral in Engineering programs at UPDC. He is the leader of Robotics and Automation Research Group, JITA, and the author of 2 patents and numerous scientific papers. His research interests are microprocessors design and test, fault-tolerant system, parallel computing, and robotics. Valle holds a master's degree in electronic engineering in 1985 and a PhD degree in electronics and computer science in 1990 from Universidad of Genova, Italy. Since 2006, he has been an associate professor in electronic engineering with the Department of Electrical, Electronic and Telecommunications Engineering and Naval Architecture at University of Genova, where he is the head of Connected Objects, Smart Materials, and Integrated Circuits, Cosmic Laboratory. In 2017, he received the Italian National Scientific Habilitation to be full professor of electronics. He's the co-author of more than 200 papers of peer-reviewed international scientific journals and conference proceedings. His research interests include biomedical circuits and system, electronic artificial sensitive skin, embedded electronic system for tactile sensors, tactile sensing system for prosthetics and robotics, neurophotic touch sensors, and wireless sensor networks. He is a member of the IEEE CAS Society. Fernando Vidal Verdú got his degree in physics, branch of electronics from University of Seville, Spain in 1988, and PhD degree in microelectronics from the University of Malaga, Spain in 1996. He's currently an associate professor at the University of Malaga. He is an author and co-author of more than 26 papers in international journals, chapters of books, and 58 papers in conference proceedings. His previous research activity was in the design of VLSI fuzzy and neurophase controllers using analog and mixed signal techniques. His current research interests are smart sensors and actuators, and specifically in tactile interfaces. We also have Professor Ali Ibrahim. He holds a master's degree in industrial control from Doctoral Schools of Science and Technologies, Lebanese University in 2009, and a dual PhD degrees in electronics and computer engineering and robotics and telecommunications from the University of Genoa and Lebanese University in 2016. From 2009 to 2013, he was a project designer in electronics in Beirut. He was postdoctoral researcher with the Department of Electronic Telecommunication Engineering and Naval Architecture at the University of Genoa. His research interests involved embedded electronic system, FPGA implementation, digital data processing, and interface electronics for electronic skin system, embedded machine learning, approximate computing, and techniques and methods for energy efficiency embedded computing. We have our coordinator of the doctoral program. Germán Fernández holds a bachelor's degree in electronics engineering from Universidad Autónoma de Colombia. He holds a master's degree in electrical engineering from Universidad de los Andes and industrial automation from Universidad Nacional de Colombia. He's also a master's in system and communication networks from the Universidad Politécnica de Valencia, Spain. He's a doctor in telecommunication at the Universidad Politécnica de Valencia. His research interest includes wireless communication and propagation modeling. His current research is focused on channel measurements and modeling in vehicular-to-vehicular communications. Now, I'm going to explain the methodology for this dissertation. It consists of 3 stages. First, Maria will have 30 minutes to present his proposal. Second, the reviewers participating in this dissertation can ask Maria questions in order to confirm that she addresses their suggestions and observations. Later, attendees with a PhD can also take part in this stage. Finally, at the end of the question time, Professor Wilson Perez, as advisor of Maria, will have time for brief feedback. Only the first stage will be streamed via YouTube. We kindly invite Maria to start his presentation. Welcome, Maria.
Thank you so much, Teacher Camilo. Let me share my screen. Good afternoon, Professor Mauricio, Professor Fernando. Good morning, professors and partners of our doctoral program and our university. I am Maria Luisa Pinto Salamanca. On behalf of my advisor, Professor Wilson Javier Perez Holguin, and my own, we thank you for attending the presentation of my doctoral proposal entitled Efficient Hardware Implementation for the Reconstruction of Contact Forces in Smart Tactile Sensing. The proposal that I am going to present today is the result of a process based on the evaluator suggestions, the related works in smart tactile sensing systems, the orientation of my advisor, and the experience of the Robotics and Automation Research Group, GIRA, at the Design and Test Research line. This is today's agenda. Firstly, I'm going to explain the issues that motivated the proposal, the state of the art and the related works. Then the research problem and the proposal contribution will be described. Next, I'll present the objectives, methodology, and previous results. And finally, I'll describe the expected results of this proposal. Replicating the sense of human touch has been a topic that has generated great interest to me even before starting the doctoral program. Currently, there are developments for humanoid robots with artificial skin, prostheses with the transmission of tactile information, tactile feedback for anthropomorphic robot grippers and robot manipulation tasks. Contributing to improving these systems through the electronic circuits opens up a wide spectrum of opportunities that generate many of my initial motivation to address these issues. The scientific community has approached the challenges involved in replicating the sense of touch by studying the multisensory perception characteristics. Multiple receivers expand in different densities and large areas which respond to variable frequencies, as well as the complex cognitive subsystems to recognize tactile interaction. All these processes have already been explained in 5 functional events that include the generation of the tactile stimulus, the stimulus recognition, and the transmission and processing the tactile information. The objective SMART has strong implications for electronic systems since it is introduced to represent the capture and hierarchical transmission of signals with a higher level of processing for responding to complex tactile stimuli in real time, which allows expanding the field of tactile sensing systems in robotic and biomedical applications. Specifically, in the tactile data decoding level, the equivalence to the last stimulus perception event is given by the processing and the extraction of structural information from the contact event. Tactile data decoding requires hardware and software to implement algorithms related to the contact information, object properties, and tactile modalities. At this level, we found some open issues that can be addressed through the combination of the hardware accelerations and data decoding algorithms. In order to address the identified open issues, we propose to exploit the efficient hardware architecture's potentialities, also based on some previous works on hardware and software implementations to haptic and teleoperation systems, thanks to the support of the researchers of Cosmic Group at the University of Genoa through the short stay carried out a year ago, we were able to focus this proposal to the reconstruction of contact forces. So, because of this proposal will be centered on the next 3 topics: efficient hardware implementation to the contact forces reconstruction in smart tactile sensing systems. Seeking to have a better understanding of the scientific community contributions to the contact force reconstruction issues, we performed a careful revision of the state of the art divided in 2 stages. First, by defining 3 equations, we did a separate search of words related to the proposal 3 main topics, followed by an analysis of the intersection of the results. To do so, the preferred reporting item for systematic reviews and meta-analysis methodology was applied. By using 2 databases, the 3 source equations were employed. We initially identified 2005 words related to smart tactile sensing systems, 94 words for efficient hardware implementations, and 73 words to contact force reconstructions ones. Next, we applied 3 filters through the screening and eligibility processes, rejecting words that did not contribute to the variables analyzing to the state of the art. Finally, we reviewed ATI complete words that contextualize the proposal. 78 efficient hardware contributions, and 49 approaches to forces reconstruction. The results of the review, the last two elements, will be detailed below. Literature allows us to establish that analytical models, machine learning techniques, and signals processing system can be implemented by software, hardware, or heterogeneous solution. The choice depends on requirements in terms of flexibility, parallelism, operating conditions, and metrics such as performance and energy efficiency. By means of efficient hardware implementation techniques, architectures are designed for application with algorithms computationally intensive or complex and stronger requirements. A hardware implementation can be considered efficient when, in addition to meeting the expected system functionality, optimal decisions for resources management and constraints compliance are also considered during the design and verification processes. The review of the works on efficient hardware implementations was carried out by crossing the variables such as applications, architectures, algorithms, computational complexity, and evaluation metrics. The implementations are applied in these fields, including machine learning, image processing, signal processing, digital design, and robotics. All these fields are characterized by specifications like high speed, real-time, complex computing, and high data volume. In the review works, the authors implement homogeneous architectures as FPGA, GPU, and ASIC, or heterogeneous as FPGA plus SoC, or CPU plus FPGA. The comparison with other architectures are also considered. The author demonstrates that algorithms with quadratic or logarithmic level of complexity can be efficiently implemented on different platforms complying GPU and FPGA. This picture depicts the identification of metrics used by the scientific community to evaluate the hardware implementation efficiency. Metrics more commonly used by the authors are hardware resource, power consumption, speed, processing time, throughput, accuracy, and precision. In the case of tactile sensing systems, hardware implementations are also considered efficient when they capture, transmit, or process tactile signals complying with some specific evaluation metrics. Some works at the level of interface electronics and tactile data decoding levels were evaluated with these metrics. The most common metric is power consumption, but performance and latency measurements are also used to define efficiency. In the literature review, it was found that the reconstruction of contact forces consists on detecting the distribution, intensity, direction of the force, and their temporal evolution through the information provided by tactile sensors. The estimation of contact forces is essential for processing other tactile properties and in the feedback or in sleep or grid control loops, which depend on the perception of real-time contact events. We define the state of the art of contact forces reconstruction by analyzing information related to applications, reconstruction approaches, tactile sensor technologies, implementations, and evaluation metrics found. The main applications that require force reconstruction approach are centered in robotic systems, including tasks such as shape recognition, robot gripper, robot sleep detection, control grasping, sleep control for hand robotics, robotic skin, human-robot interaction, soft robots, wearable assisted robots, and stiffness classification. Other works also report algorithms for biomedical device, prosthetic hands, haptic assistive, and human-machine interface. Additionally, approach to novel tactile sensors with flexible and visio-based features are also considered. The reconstruction of contact force favors the analysis of those object properties, and some works also demonstrate that the shape recognition from forces vectors. Therefore, the estimation of contact force presents a direct way to increase the level of hierarchy in tactile data processing. State of the art shows about 40 different contact forces reconstruction approaches. The author reports analytical models based on physical laws or model-driven, machine learning frameworks or data-driven, mixed of semi-analytical models with numerical methods and stochastic processes, Such approaches are implemented employing software and hardware alternatives, considering the types of tactile sensors found. Most of the contributions focus on vision-based sensors and biomimetic sensors. Sensor arrays are based on transduction technologies as capacitive, piezoresistive, magnetic, ceramic, and piezoelectric. Some vision-based sensors, biomimetic and piezoresistive, are commercially available, and others are at development stage. It is important to take into account that the sensor type does not define the reconstruction approach to be used. So sensors with similar transduction technology employ different types of approaches. The research problem of this proposal is formulated considering the reliability, portability requirements in smart tactile sensing systems and the rules defined by WOSCO and other authors, which establish that the processing system for contact modeling must depend on the contact event itself, the execution time must be predictable, and that the solution must scale to multiple contact areas. However, based on the results of the state-of-the-art in this proposal, the generalization of the contact forces approach comprises in addition the approach application, regardless of the transduction technology, while the implementation efficiency features are based on a set of evaluation metrics, not only the execution time. In the literature review, different algorithms were found, regardless of the type of sensor and the approach employed. The decoding of the contact force event is relative to the sensor type. Therefore, most contributions cannot be generalized because they depend on the type of information provided by the tactile sensor. And in database models, there is also dependency on the training data. So these are some examples of algorithms for vision-based sensors. While these are the case for biomimetic array and non-array tactile sensors. These are different contact events algorithms for the same transduction technology. However, an exception of that is the work reported by Professor Seminara and other authors, in which the work made a force estimation using a model-driven approach that can be used on different transduction technologies. Most of the implementation for contact force reconstruction approaches are based on software development for PC or workstations, without including portability considerations and restrictions on data memory, processing time, power consumption, system setup size, or cost. The hardware implementations found are based on FPGAs and system and modular architectures. Some parameters evaluated were these, which were established according to compliance with system requirements. Only in a few cases, the works reported in the literature consider the evaluation of latency, area occupation, performance, and modularity. Taking into account the concept of efficiency, it was found that in the previous work, the evaluation of the model has only been given in terms of the accuracy in the first prediction. Force reconstruction approach do not address portability, but rather reliability requirements. The works reported in the literature do not consider performance metrics to evaluate the system efficiencies such as power consumption and on real-time execution. Regarding scalability, the authors reported difficulties in applying contact force reconstruction to large sensing areas. Two examples for non-commercial vision-based sensors are these. Taking into account these sensors, the estimation of the forces depends on the movement of a maker's matrix in a sequence of images. These sensors have high tactile resolution, and as in the biomimetic sensors, they have a contact medium with soft deformable properties that facilitate the modeling and soft and dynamic contacts. However, challenges remain due to the need for complex image processing algorithms and the size of the sensors. In the sensor arrays case, the works reported in the literature include not commercial options with flexible and deformable features over thin layers. Some errors reported were these: generally less than 20 20 by 20 millimeters. Also, most sensor arrays do not measure force. So additional processing steps are required for vector reconstruction from the discrete information provided by the transduction. So the literature review, we found that efficient hardware implementation for algorithms with high computational complexity and strict operation restrictions. Most of the context force reconstruction approach found were implemented just in software and applied to small contact areas without considering portability issues. Hardware implementations are currently present in the interface electronics and tactile data COVID-11, and two of those works are related to the context force reconstruction. However, such works have not been evaluated under real-time execution and power consumption metrics. In this context, the research question for this proposal is this: how carry out an efficient hardware implementation to the reconstruction of contact forces approach for sensor arrays in the context of smart tactile sensing oriented to robotics and biomedical applications under low latency, low power consumption, and real-time execution constraints? In the proposal hypothesis, we assume that by performing an efficient implementation of the hardware dedicated to the contact forces reconstruction, guided by a careful evaluation of metrics such as latency, power consumption, and real-time execution, it is possible to improve the sensor emulation characteristics to a smart tactile sensing system based on tactile sensor arrays, contributing in this way to expand the fields of application of artificial skin technology. The hardware implementation will be based on the modeling of static and single contact events on a non-deformable flat surface, uses as input tactile information captured by tactile sensor arrays over different contact areas and using different transduction technologies. By analyzing the intersection of the three topics of this proposal, we found the next research opportunity: the need for efficient hardware implementations for the reconstruction of contact forces in smart tactile sensing systems that ensure low latency, low power consumption, and real-time operation, and help to improve the emulation of the sense of touch in artificial skin systems to robotics and biomedical applications. Retaking the rules applied in the problem statement, in this proposal, we will implement a contact force reconstruction approach for tactile sensor arrays, which provide discrete information of pulses regardless of the transduction technology. In this sense, our hardware implementation will be considered efficient when, in addition to the correctly calculating to the forces estimation, it will comply with the specific evaluation methods that guarantee portability and reliability characteristics. To fulfill with this, we'll use design techniques aiming to exploit the inherent parallelism of software hardware platforms. We'll use heterogeneity approach to make the best of each platforms. We'll take advantage of approximate compute to reduce area and power consumption, as well as the use of hardware and software co-design techniques to gain flexibility and facilitate the system implementation. We will also evaluate different sensor arrays size and sensing area in electronic skin applications. We'll study the impact on computational complexity and resource consumption of modifying sensor size and resolution, as well as the non-linearity effects. So to achieve that, we define these objectives. A general objective, we want to design and implement efficient hardware architectures for the reconstruction of contact force in the context of a smart tactile sensing system. To get this goal, we are going to define a smart tactile data processing system to the hardware implementation of a contact force reconstruction approach based on tactile sensor arrays in robotic or biomedical applications. Design a hardware implementation for the defining contact force reconstruction approach. Perform the design verification, testing stage, and implementation for the hardware architectures for the force reconstruction approach. And evaluate the efficiency of the hardware implemented by validating its application in the smart tactile sensing systems. The proposed methodology to face the objectives corresponds to a research applied type and comprise 4 main stages: system identification, hardware design, design verification, prototyping, implementation and testing, and finally, system validation. In the first stage, the system specifications include the following activities: identification of design specifications at the functional level, selection of a contact force reconstruction approach, considering the modeling of static and single contact events on a non-deformable flat surface. Lay will characterize the contact force reconstruction approach through a mathematical analysis, simulations, and software implementations. By defining the input data requirements, we will take into account input data magnitudes, size and data types, transduction technologies, sensing area size, and nonlinearity characteristics. We will obtain the input data by accessing to data sets of tactile sensor arrays available online on the academic research community and finite element modeling simulations. At the end of the first stage, the smart tactile data processing system specifications should be defined, considering the number and type of input and outputs, time, power constraints, and some preliminary hardware characteristics. The second stage will be focused on the hardware design. The activities of this stage include a review of the design techniques commonly used to address the phishing hardware implementations. The high-level system design will be guided by the previously defined evaluation metrics. In the analysis of the implementation requirements, we will address arithmetic operations requiring scalability effects, computational complexity, and data resolution. We propose an initial resolution at the fixed point at 32 bits. However, this will depend on the system behavior. Subsequently, we will define tasks to be parallelized considering the use frequency, computational complexity, and execution time. After, we will select the hardware architecture considering the level of parallelism or heterogeneity. Some architectures to be used during the development of this proposal are those based on FPGA SoC and FPGA MP SoC. We will consider the custom design and implementation of IP cores for hardware accelerations. In order to improve the efficiency, we will apply techniques as approximate computing and hardware software co-design. After, we will develop the subsequent activities related to the low-level design and system modeling. The first stage consists of the design verification, prototyping, implementation, and system testing. The final hardware implementation will be defined by the hardware prototyping evaluation. The hardware platforms to be used in the development of this proposal range from FPGA SoCs to ASICs. The system test will be based on the evaluation of the metrics defined. The last stage, center of the system validation, will be limited to development of the finite element modeling simulations, including the design and execution of experiments to validate the force reconstruction approach. These experiments will consider the forces accuracy measurement and analysis of nonlinearity effects and the results comparison between hardware and software implementations. Simultaneously, of the development of the main fourth stage, we plan to develop activities related to the results sharing that include progress reports, a doctoral internship, the preparation and submission of conference papers and journal papers, and finally, the doctoral dissertation. Proposed activities will be developed in 30 months. In the schedule, the approach characterization, system specification, high-level system design, test, and validation activities were identified as a critical path. The activities made to date are the identification of the design specification at the functional level, the selection and characterization of a model-driven contact force reconstruction approach. Regarding to the functional specifications, the force reconstruction problem was defined in terms of the discretization of values supplied by sensors and the implications that this has on the hardware implementation. It was found that vector fields of forces must be estimated from scalar values pressures in the case of commercial sensors, and that the modeling of contact event established the scope of the implementation. Consequently, bearing in mind the evaluator suggestions, the proposal was delimited to modeling a single and static contact event on a flat, not deformable surface. Among the different approaches we have selected by analytical model reported by Professor Seminara and other authors from University of Genoa. Such a model proposed the reconstruction of 3D contact force distribution to the surface of soft layer by means of the model of the normal stress data recovered from a piezoelectric sensor arrays. That approach is based on the elastic half space problem, the discretization of ill-post inverse problems, the Green's function, and the busyness equation. That model has been implemented in software and hardware, allows to change the size and sensor resolution, and includes latency and accuracy metrics. In the selected approach, we have analyzed the modeling of content mechanics, the mathematical expressions, and the model constraints that include static contact, flat surface, and small deformations. We have already identified the algorithm phases to some scalability effects in the hardware resource, memory management, and data representation formats. We have currently made a software implementation in MATLAB, which is ready to be validated by the scientific community, and with contact events data obtained by datasets or finite element modeling simulations. This is our next step. We hope that the proposed stage will allow us to have the characterization of the contact force reconstruction approach, the design and implementation on a hardware architecture for the contact force reconstruction evaluated under the chosen metrics, the validation of the proposed implementation through experiments based on different adduction technologies and sensor array size, besides complies with the chosen metrics that allow us to evaluate the contribution of the proposal in terms of generalization, efficiency, and scalability. We hope that these results facilitate the inclusion of complex contact event characteristics that can be further extended to other types of tactile sensors. Additionally, it is expected to contribute to the state-of-the-art in the tactile sensing systems through efficient hardware implementation and the arising of new works related to this proposal. This brings me to the end of my presentation. Finally, I would like to thank you to the evaluator for the suggestions and comments of the proposal. Thanks everyone for your attention.
Very much, Maria, for your dissertation. Now, we just want to say that on behalf of the doctoral program in Engineering and Electronics Engineering Graduate School, we thank everyone who followed this presentation via YouTube. We are very committed to our academic process and are research-oriented towards solving contextual problems. Our doctoral programs promote three fundamental pillars: research as a route to find solutions to local problems with a global view, self-management that encourages autonomy and self-confidence of our students, and networking that promotes collaboration with the international community. We hope that you have enjoyed this event and that its content has been meaningful to you. Thank you very much to the people who follow this streaming via YouTube.